Let us settle in with a quiet idea. In linear algebra, we often meet linear transformations as rules that take vectors to other vectors. We picture them as actions on space, stretching, compressing, flipping, shearing, rotating, or some commixture of these behaviors. And when we first learn about linear maps, they can feel complicated. A transformation might send one direction to a different direction, and another direction somewhere else, and everything seems to blend together. Eigentheory is one of the most gentle ways of finding order inside that complexity. It asks a simple question, repeated patiently in many forms. Is there any direction in space that the transformation does not truly turn, but only stretches, shrinks, or flips? That is the heart of what we will explore. We will move slowly through eigenvalues and eigenvectors, and then into diagonalization, and then into the appearance of complex numbers. After that, we will introduce inner products, which is how geometry enters the story in a precise way. And finally, we will talk about orthogonality, projections, and the procedure called Gram-Schmidt, which turns an untidy set of directions into a tidy one. As we go, it is worth repeating, the goal is simplification. Not simplification by ignoring details, but simplification by choosing the right viewpoint, the right coordinates, the right language for the transformation that is already there. Let us begin with invariant directions. A linear transformation acts on vectors. But a vector is not only a point, it also represents a direction and a magnitude. And when we apply a linear map to a vector, the result may point in a different direction. An eigenvector is a special vector, not because it is large or small, but because of how it behaves under the transformation. When you apply the transformation to an eigenvector, the result points in the same direction as the original. The transformation does not rotate that vector into a new direction. Instead, it only changes its length and possibly reverses its orientation. So an eigenvector is a direction that is preserved by the transformation. The map may stretch along that direction, or compress along that direction, or flip it to face the opposite way, but it does not mix it with other directions. And the eigenvalue is the number that describes how much stretching or shrinking happens in that direction. If the eigenvalue is positive and bigger than 1, the direction is stretched. If it is between 0 and 1, the direction is compressed. If it is negative, the direction is flipped as well as rescaled. If it is exactly 1, the vector stays exactly the same. If it is 0, the vector is collapsed to the 0 vector, so that direction is crushed entirely. It is worth repeating this slowly. Eigenvectors are invariant directions. They are directions that remain directions of themselves. And eigenvalues tell us the fact by which the map scales those directions. Why is this so revealing? Because it shows the internal geometry of the map. A linear map can be thought of as having preferred directions it treats in a pure way. Instead of mixing directions, it acts cleanly along them. Let us return to a few familiar transformations to see this in a calm, repetitive way. First, consider a pure scaling transformation, one that stretches every vector by the same factor. In that case, every direction is an eigendirection, because no direction is rotated into another. Every vector is simply lengthened or shortened, and the eigenvalue is the common scaling factor. This is the simplest case, and it teaches the basic idea. An eigenvector is a direction that the map does not twist. Now consider a shear transformation in the plane, the kind that slides points horizontally in proportion to their vertical coordinate, while leaving vertical position unchanged. In such a transformation, one direction is special, the horizontal axis. Vectors pointing purely horizontally often remain purely horizontal, perhaps unchanged or perhaps scaled, depending on the shear. Meanwhile, other directions are generally tilted into new directions. So for a shear, eigenvectors may exist, but they are fewer, and they highlight the axis along which the shear has a clean effect. Now consider a rotation in the plane, rotating every vector by a fixed angle that is not a full half-turn. In that case, in real two-dimensional space, no non-zero vector keeps its direction. Every direction is turned into a different direction, so there are no real eigenvectors. This is an important lesson. Eigenvectors may not exist in the real setting, even when the transformation is perfectly nice and geometric. The absence of real eigenvectors is not a failure of the transformation, but a sign that the transformation's inner behavior is rotational rather than stretching along fixed lines. Let us pause and reflect. A linear transformation can be understood by asking, does it have directions that are preserved? If yes, those are eigendirections. If no, then the transformation's behavior is more like rotation or mixing, and we need a different language, perhaps involving complex numbers, which we will come to later. But even before complex numbers, it is helpful to remember that eigenvectors are about reducing mixing. When you find eigenvectors, you find directions along which the map acts independently. That phrase independently will return again and again, because it leads us naturally to diagonalization. Diagonalization is one of the most soothing ideas in linear algebra because it is about choosing the right perspective. A linear transformation can be represented by a matrix once we choose a basis. The same transformation can have very different matrices in different bases. Some matrices look messy, with many non-zero entries. Others look simple. A diagonal matrix is among the simplest. In a diagonal matrix, the only possibly non-zero entries are those that describe what happens to each basis direction itself. The transformation sends each basis vector to a scalar multiple of itself, and nothing mixes with anything else. So diagonalization means this, finding a basis of the space consisting of eigenvectors of the transformation, so that, in that basis, the matrix becomes diagonal. In that special coordinate system, the transformation acts independently on each coordinate direction. Let us say this again in slower words. Diagonalization is the art of finding a coordinate system where the transformation does not mix coordinates. Each coordinate axis becomes an eigendirection. Then the transformation becomes a list of independent scalings, one scaling for each axis. This is why diagonalization is sometimes described as decoupling into independent modes. Each eigenvector is a mode, a pattern that evolves without mixing with others. The transformation simply scales that pattern. And this is not only aesthetically pleasing. It has practical consequences. When a transformation is diagonal in some basis, it becomes easy to understand repeated applications of the transformation. Applying it again and again simply scales each coordinate again and again. This is essential in studying discrete dynamical systems, difference equations, and many numerical procedures. Now, when does diagonalization work? It works when we can find enough eigenvectors to form a basis. That means we need as many linearly independent eigenvectors as the dimension of the space. Sometimes we find fewer. Sometimes eigenvectors exist, but not enough to span the entire space. Then diagonalization fails, not because eigenvectors are meaningless, but because the transformation has some internal coupling that cannot be eliminated by mere change of basis. Let us pause and reflect again. The dream is, find a basis of eigenvectors, and then the transformation becomes diagonal, meaning perfectly decoupled. The reality is, sometimes we can do that, and sometimes we cannot. When we cannot, the map still has structure, but it requires more subtle normal forms. Even so, the diagonalizable case is worth lingering on, because it teaches the guiding idea the best basis is the one aligned with the transformation's natural directions. It is worth repeating, diagonalization is not a trick. It is a conceptual change. It means we stop insisting on our original coordinate axis, and instead align ourselves with the geometry that the transformation itself prefers. Now, what if the transformation's preferred behavior is rotation? In that case, real eigenvectors may not exist, and the diagonalization story over the real numbers does not begin. But the transformation still has internal geometry. We just need a richer number system to express it cleanly. That brings us to complex eigenvalues. Let us approach complex eigenvalues with patience. Many students first see them as a technical complication. But in eigentheory, complex numbers often appear not as an artificial invention, but as the most natural language for certain real behaviors. Consider again a rotation in the plane. Over the real numbers, no direction is preserved. Every non-zero vector is turned into another direction. So there are no real eigenvectors. But the rotation is extremely structured. It is not chaotic. It rotates every vector by the same angle. That is a clean, uniform behavior. Complex numbers allow us to describe that uniform rotation as a kind of scaling, but scaling in a richer sense, scaling combined with turning. A complex eigenvalue can be thought of as encoding two things at once, a change in magnitude and a change in angle. In other words, it encodes stretching and rotation together. So even though real eigenvectors do not exist for a rotation, complex eigenvectors do. And complex eigenvalues capture the essential behavior of the rotation in a way that is algebraically simple. It is worth repeating, complex structure can encode real geometry. Complex eigenpairs are not telling you that the real transformation is somehow complex in a mysterious way. They are telling you that the transformation has a rotational component, and complex numbers are a natural coordinate system for rotation. Now let us connect this to oscillations, another theme where complex numbers arise naturally. Many systems in physics and engineering exhibit oscillatory behavior. Oscillations involve repeated rotation in a plane of states. Complex eigenvalues often correspond to that, a motion that circles around, possibly shrinking inward or expanding outward as it rotates. In a real vector space, complex eigenvalues come in pairs. A complex eigenvalue and its complex conjugate appear together. The associated complex eigenvectors also come in a paired structure, and from these pairs, we can extract a real invariant plane, a two-dimensional real subspace that is preserved by the transformation. Within that plane, the transformation behaves like a rotation combined with scaling. Let us say that again gently. When you see complex eigenvalues for a real matrix, you can interpret them as saying there is a two-dimensional real subspace where the transformation acts like a rotation and scaling. The complex numbers are a compact way of describing what is really happening in that plane. So complex eigenvalues are not a departure from geometry. They are a return to geometry, but with better language. Let us pause and reflect. Eigenvectors are invariant directions when those exist. Complex eigenvectors, when real ones do not exist, point us toward invariant planes, where the transformation behaves like rotation and scaling together. This prepares us for the next shift. Up to now, we have talked about directions and scaling, but we have not yet had a precise way to speak about angles, lengths, and best approximation. For that, we need extra structure, an inner product. A vector space, by itself, is an algebraic object. It lets us add vectors and scale vectors. It does not, by itself, tell us what it means for a vector to belong, or for two vectors to meet at a right angle, or for one vector to be close to another. To speak about length and angle, we need a rule that takes two vectors and produces a real number that measures their interaction. This rule is called an inner product. The most familiar inner product in ordinary Euclidean space is the dot product, but it is helpful to think more generally. An inner product is any function that takes two vectors and returns a real number, in a way that satisfies certain properties that make geometric sense. Let us list these properties slowly. First, symmetry. The inner product of the first vector with the second is the same as the inner product of the second with the first. This fits the idea that the interaction between two vectors should not depend on the order. Second, linearity in one argument. If you fix one vector, then the inner product depends linearly on the other. That means if you add vectors or scale vectors in that slot, the inner product behaves in the expected linear way. Third, positivity. The inner product of a vector with itself is never negative, and it is zero only when the vector itself is the zero vector. This makes it possible to define length, because length should be non-negative, and only the zero vector should have zero length. From these properties, we can define the length of a vector as the square root of the inner product of the vector with itself. And we can define angles through a relation involving the inner product as well, though we do not need to write that relation symbolically. Conceptually, the inner product measures how much two vectors point in the same direction. It is worth repeating, geometry needs extra structure. A vector space is not automatically a geometric space. An inner product is what turns algebraic vectors into geometric objects with lengths and angles. This will matter deeply when we discuss orthogonality and projections, because those ideas depend entirely on having a notion of angle and distance. Let us move gently into orthogonality. Orthogonality is one of the commonest ideas in mathematics. Two vectors are orthogonal if they have no overlap in influence, meaning their inner product is zero. In ordinary Euclidean intuition, orthogonal vectors meet at a right angle. But it is worth repeating that the inner product is the real definition. Orthogonality means the inner product is zero. The right angle picture is a helpful mental image in familiar spaces, but the definition is the one that generalizes. When two vectors are orthogonal, you can think of them as independent directions in a geometric sense. If you move along one, you do not move along the other. Their contributions do not interfere. Now, projections. A projection is a way of taking a vector and finding its best approximation inside a given subspace. Suppose you have a subspace such as a line through the origin, or a plane through the origin, or some high-dimensional subspace. You have a vector that may not lie in that subspace. You want to replace it with a vector inside the subspace that is as close as possible to the original. The inner product gives us a way to define as close as possible because it gives us length, and therefore distance. The best approximation is the one that minimizes the distance between the original vector and the approximating vector in the subspace. The projection has a defining geometric property. The difference between the original vector and its projection is orthogonal to the subspace. In other words, when you subtract the projection from the original, the leftover part points entirely in directions that have zero inner product with every vector in the subspace. Let us say that again, because it is worth repeating. The projection splits the vector into two parts, one part inside the subspace and one part orthogonal to it. The orthogonal part is what cannot be captured by the subspace. The part inside is what the subspace can explain. This is why projections are central in least squares problems, approximation theory, statistics, and numerical methods. Whenever you want the best fit inside a smaller model, you are projecting onto a subspace. Let us pause and reflect. Orthogonality means no overlap according to the inner product. Projection means the best approximation in a subspace, characterized by the error being orthogonal to that subspace. We are beginning to see a theme. Choosing good direction simplifies everything. Eigenvectors simplify linear transformations. Orthogonal directions simplify geometry and approximation. And the best case is when we have a basis that is not only made of helpful directions, but also mutually orthogonal and normalized. That leads to orthonormal basis. An orthonormal basis is a basis where every vector has length 1 and every pair of distinct basis vectors is orthogonal. This is a particularly clean situation. When a basis is orthonormal, coordinates become simple to interpret. The coefficient of a basis vector in a decomposition is exactly the inner product with that basis vector. There is no need to solve complicated systems just to find coordinates. The geometry and the algebra align perfectly. It is worth repeating why this is soothing. In an orthonormal basis, each basis direction is independent in the stronger sense, orthogonal, so it does not overlap with others, and normalized, so its length is 1, making coefficients directly comparable. But we often begin with a basis that is not orthonormal. Perhaps it is just any linearly independent set. It spans the space, but it may be skewed, with vectors pointing partly in the same directions and with different lengths. Gram-Schmidt is a procedure that takes such a linearly independent list and converts it into an orthonormal list that spans the same subspace step by step. The spirit of Gram-Schmidt is simple, even if computations can be long. You start with the first vector and normalize it to length 1. Then you take the second vector and remove the part of it that lies along the first. What remains is orthogonal to the first. Then you normalize that remainder. Then you take the third vector and remove the parts that lie along the first two orthonormal vectors. What remains is orthogonal to both. Then you normalize it. And you continue. Let us say this again in common words. Gram-Schmidt repeatedly does two things. It subtracts projections to remove overlap, and it normalizes the set length to 1. Subtract projection, normalize. Subtract projection, normalize. In this way, each new direction is cleaned of components that would interfere with the earlier directions. The result is an orthonormal basis for the same subspace you started with. Nothing is lost in terms of span. You have simply replaced a messy coordinate system with a clean one. And this procedure has a stable meaning even when computations are technical. The meaning is always, remove overlap with what you already have, and then standardize the result. This is deeply connected to the projection idea we already discussed. Gram-Schmidt is like repeatedly taking a vector and splitting it into a part explained by the existing subspace in a leftover orthogonal part, and then keeping that leftover as a new direction. So Gram-Schmidt is not random. It is built from projection, and projection is built from orthogonality, and orthogonality is built from the inner product. Let us pause and reflect again. We began with eigenvectors, which are directions preserved by a transformation. We moved to diagonalization, which is choosing a basis of such directions so the transformation becomes decoupled. We then saw that complex eigenvalues arise naturally when the real geometry is rotational. Then we introduced inner products to speak about length and angle. And then orthogonality and projections to speak about independence and best approximation. And finally orthonormal bases, which make coordinates transparent, and Gram-Schmidt, which constructs such bases. Everything is, in a sense, about choosing the right directions. Let us end by gathering the main ideas quietly, repeating them in a unified way. Eigenvectors are invariant directions of a linear transformation. When you apply the transformation to an eigenvector, the result stays in the same direction, only scaled, possibly with a flip. The eigenvalue is the scaling factor that describes that stretching, shrinking, or flipping. This reveals the internal geometry of the transformation. Instead of seeing the map as something that mixes everything, eigenvectors show directions where it acts purely. Diagonalization is the act of choosing a basis made from those eigenvectors, when possible. In that basis, the transformation becomes as simple as possible, each coordinate is scaled independently. The transformation is decoupled into modes that do not interact. Sometimes real eigenvectors do not exist, especially in transformations involving rotation. Complex eigenvalues and eigenvectors then appear naturally, not as a strange trick, but as a clean way to encode rotation and oscillation. In real spaces, complex eigenpairs correspond to real invariant planes where the map behaves like rotation combined with scaling. To speak about geometry more generally, we introduce an inner product, which gives a precise meaning to length and angle. A vector space becomes a geometric space only after we add this extra structure. Symmetry, linearity, and positivity make the inner product behave like a sensible geometric measure. Orthogonality then means zero overlap, the inner product is zero. Projections use this geometry to give best approximations in subspace. The projection is the element of the subspace closest to the vector, and the area is orthogonal to the subspace. Orthonormal bases bring maximum clarity. Each basis vector has length 1, and different basis vectors are orthogonal. Coordinates become clean and directly interpretable. And Gram-Schmidt is the patient procedure that turns an arbitrary linearly independent list into an orthonormal one, by repeatedly removing projections and normalizing. It is worth repeating one last time, linear algebra often becomes gentle when we stop fighting the structure of the problem and instead align our viewpoint with it. We look for invariant directions, orthogonal directions, and well-chosen bases. We do not change the transformation or the space. We simply choose a common coordinate system, one that lets the underlying behavior speak plainly. And with that, we can rest in the thought that much of mathematics is like this, a search for the right language, the right viewpoint, and the right set of directions in which complexity becomes quietly understandable.